Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The cosmos, a realm of seemingly infinite expanse, presented early astronomers with a profound challenge accurately gauging the distances to celestial objects. Before the advent of sophisticated techniques, astronomers primarily relied on the method of parallax, a geometric principle where the apparent shift in a star's position is measured against the backdrop of more distant stars as Earth orbits the Sun. This method, while effective for relatively nearby stars, becomes increasingly unreliable as distances increase, owing to the diminishing angle of parallax, which eventually becomes too small to measure with any degree of precision. This limitation severely hampered our understanding of the true nature and scale of the universe. Into this arena of uncertainty stepped Ejnar Hertzsprung, a Danish astronomer whose meticulous observations and insightful analyses would lay the groundwork for a revolution in stellar astrophysics. Born in Copenhagen in 1873, Hertzsprung embarked on a scientific journey marked by a keen eye for detail and a willingness to challenge prevailing assumptions. He initially pursued a career in chemical engineering, but his fascination with astronomy soon led him to dedicate his life to unraveling the mysteries of the stars. Hertzsprung's early research focused on the colors of stars, an area that might seem tangential to the problem of distance measurement. However, he recognized that a star's color, indicative of its surface temperature, could potentially serve as a proxy for its intrinsic luminosity, the total amount of energy a star radiates into space. The challenge lay in establishing a reliable relationship between these two properties. His seminal 1905 paper, titled Der Strahlen der Sterne, translated as On the Radiation of Stars, marked a pivotal moment in this endeavor. This work directly addressed the fundamental problem of stellar distance determination, particularly for stars beyond the reach of traditional parallax measurements. Hertzsprung astutely observed that stars exhibiting similar colors did display a wide range of brightnesses. He proposed that color indices, derived from photographic magnitudes measured in different colors, could offer a valuable tool for estimating stellar distances. Hertzsprung's methodology involved painstakingly measuring the photographic magnitudes of stars through different colored filters. These magnitudes were then converted into color indices by subtracting the magnitude in one color from the magnitude in another. The resulting color index provided a quantitative measure of the star's color, with bluer stars having smaller color indices and redder stars having larger ones. He reasoned that if a correlation could be established between color index and absolute magnitude, a measure of intrinsic luminosity, then the distance to a star could be estimated by comparing its apparent magnitude, how bright it appears from Earth, with its absolute magnitude. A tangible example of his early work can be found in his analysis of stars within the Pleiades star cluster. Hertzsprung meticulously collected and analyzed photographic data for these stars, calculating their color indices and attempting to discern any patterns or relationships. While his initial efforts were hampered by the limited data available at the time, they laid the foundation for his subsequent breakthroughs. The concept of using color indices to estimate stellar distances was directly influenced by the work of Norman Robert Pogson, a British astronomer who formalized the magnitude scale in the 19th century. Pogson's scale, which defines the difference of 5 magnitudes as corresponding to a factor of 100 in brightness, provided the quantitative framework necessary for Hertzsprung to develop his color index method. Without Pogson's standardized magnitude system, comparing and quantifying stellar brightnesses across different colors would have been far more challenging. Hertzsprung's early work on color indices, while not immediately providing a definitive solution to the distance problem, had a profound impact on the field of astronomy. His meticulous observations and insightful analyses paved the way for a deeper understanding of stellar properties and their interrelationships. His 1905 paper served as a catalyst for further research, inspiring other astronomers to explore the connection between color, luminosity, and distance. One astronomer directly influenced by Hertzsprung's work was Henry Norris Russell, an American astronomer who, independently of Hertzsprung, was also investigating the relationship between stellar properties. Russell, upon learning of Hertzsprung's findings, recognized the significance of his color index method and its potential for unlocking the secrets of stellar evolution. This initial influence eventually led to a collaboration between Hertzsprung and Russell, culminating in the development of the Hertzsprung-Russell diagram, a cornerstone of modern astrophysics. This diagram graphically plots the absolute magnitudes of stars against their spectral types or color indices, revealing distinct patterns and relationships that provide invaluable insights into the life cycles of stars. While the details of the Hertzsprung-Russell diagram are beyond the scope of this initial exploration, it is important to acknowledge that Hertzsprung's early work on color indices was a crucial stepping stone in its development. The legacy of Hertzsprung's initial foray into stellar astronomy extends far beyond the historical context of early 20th century astrophysics. Color indices, refined and enhanced with modern technology, remain a fundamental tool for astronomers today. Sophisticated photometric systems, employing a wide array of filters spanning the electromagnetic spectrum, allow astronomers to measure stellar colors with unprecedented precision. These color indices are used to estimate stellar temperatures, chemical compositions, and distances, as well as to identify exotic objects such as quasars and brown dwarfs. The principles laid down by Hertzsprung over a century ago continue to guide astronomical research, demonstrating the enduring power of careful observation and insightful analysis. Though the techniques have evolved significantly, the underlying concept of using a star's color as a proxy for its intrinsic properties remains a testament to Hertzsprung's pioneering vision. The implications of using color indices to estimate stellar properties were profound, yet they also hinted at a deeper complexity within the stellar realm. Hertzsprung's meticulous observations revealed a startling truth of stars sharing similar colors and therefore similar surface temperatures could exhibit dramatically different luminosities. This revelation challenged the prevailing assumption that color alone could definitively determine a star's intrinsic brightness. He directed his attention toward galactic star clusters, gravitationally bound groups of stars born from the same molecular cloud as ideal laboratories, to investigate this phenomenon. Specifically, the Hyades and Pleiades clusters became focal points of his research. Hertzsprung observed that within these clusters, stars of comparable color displayed a considerable range in brightness. Some stars were intrinsically luminous, radiating vast amounts of energy, while others, despite possessing the same surface temperature, were significantly fainter. This disparity in luminosity among stars of similar color suggested the existence of distinct stellar populations, a concept that would revolutionize our understanding of stellar evolution. The challenge was to decipher the underlying cause of this luminosity difference. Were these stars at different distances, thus affecting their apparent brightness, or were there genuine variations in their intrinsic properties? To address this problem, Hertzsprung embarked on a systematic campaign to determine the distances to individual stars within the Hyades and Pleiades clusters. He employed a combination of techniques, including statistical parallax, which had been pioneered by Jacobus Kapteyn. Statistical parallax utilizes the proper motions, the apparent angular movement of stars across the sky over time, and radial velocities, the speed at which stars are moving towards or away from us, to estimate their distances. By analyzing the collective motions of a group of stars, astronomers can statistically infer their average distance. Kapteyn's work provided the mathematical framework for relating these stellar motions to distance estimates. Hertzsprung meticulously measured the proper motions and radial velocities of numerous stars within the Hyades and Pleiades. From these measurements, he derived estimates of their distances. Crucially, he found that even after accounting for distance variations, a significant luminosity difference persisted among stars of similar color. This led him to propose the existence of two distinct classes of stars, dwarf stars and giant stars. Dwarf stars, as the name suggests, were relatively small and faint, possessing modest luminosities. Giant stars, on the other hand, were much larger and brighter, radiating significantly more energy. Hertzsprung theorized that these differences in size and luminosity were related to the stars' evolutionary stages. He proposed that stars evolve over time, changing their physical properties as they exhaust their nuclear fuel. A tangible example of Hertzsprung's work can be seen in his observations of the star Alice in the Pleiades cluster. Alice is a B-type star, indicating Cepheid, blue surface temperature. Hertzsprung observed that while Alice was relatively bright, other B-type stars in the Pleiades exhibited a much wider range of luminosities. Some were significantly fainter than Alice, suggesting they were dwarf stars, while others were considerably brighter, indicating they were giant stars. Similarly, in the Hyades cluster, Hertzsprung identified both dwarf and giant stars of similar color. For instance, he studied several G-type stars in the Hyades, stars with surface temperatures similar to our Sun. He found that some of these G-type stars were much fainter than the Sun, classifying them as dwarf stars, while others were significantly brighter, designating them as giant stars. The star 51 Tauri, a G5 giant star in the Hyades, serves as a specific example. Its luminosity is considerably higher than that of the Sun, demonstrating the existence of luminous giants within the cluster. Hertzsprung's meticulous analysis extended beyond specific stars. He recognized that the distribution of dwarf and giant stars within the clusters held important clues to stellar evolution. He theorized that stars initially form as dwarf stars and then, through various nuclear processes, eventually evolve into giant stars. This hypothesis, though simplified compared to our modern understanding of stellar evolution, represented a groundbreaking step in unraveling the life cycles of stars. The methodology Hertzsprung employed to distinguish between dwarf and giant stars relied heavily on accurate distance determinations. He understood that errors in distance estimates could significantly affect luminosity calculations. Therefore, he meticulously refined his techniques, incorporating new data and improving his statistical analysis. He also recognized the importance of accounting for interstellar extinction, the dimming of starlight caused by dust and gas in interstellar space. Interstellar extinction can make stars appear fainter than they truly are, leading to inaccurate luminosity estimates. Hertzsprung's work on stellar populations laid the foundation for future research in stellar astronomy. His recognition that stars of similar color could have vastly different luminosities challenged the prevailing view of stars as a homogeneous population. This insight paved the way for a more nuanced understanding of stellar evolution and the diversity of stars in the universe. His categorization of stars into dwarfs and giants provided a crucial framework for organizing and interpreting stellar data. Walter Baade directly built upon Hertzsprung's work in the 1940s, leading to the identification of distinct stellar populations within galaxies. Baade recognized that galaxies contain two primary stellar populations, population I and population 42, each with distinct characteristics and evolutionary histories. Population I stars are typically found in the spiral arms of galaxies and are relatively young, yet luminous. Population 42 stars, on the other hand, are found in the galactic halo and globular clusters and are older, cooler, and less luminous. Baade's discovery of these distinct stellar populations revolutionized our understanding of galaxy formation and evolution. While Baade's specific findings regarding stellar populations are distinct, the conceptual groundwork laid by Hertzsprung was undeniably pivotal. The concept of stellar populations remains a cornerstone of modern astrophysics. Astronomers continue to study the properties and distribution of different stellar populations to unravel the mysteries of star formation, stellar evolution, and galaxy formation. Modern telescopes and sophisticated instruments allow astronomers to probe stellar populations in unprecedented detail, revealing intricate patterns and subtle variations that were unimaginable in Hertzsprung's time. The legacy of Hertzsprung's work on stellar populations extends far beyond its immediate impact. His meticulous observations, insightful analysis, and groundbreaking ideas continue to inspire and guide astronomical research. The distinction between dwarf and giant stars, initially based on simple color and luminosity measurements, has evolved into a sophisticated framework for understanding the diversity and evolution of stars in the universe. The principles he established over a century ago remain relevant today, demonstrating the enduring power of scientific curiosity and the transformative potential of careful observation. Hertzsprung's investigations extended to the captivating realm of Cepheid variable stars. Celestial beacons whose periodic brightness fluctuations hold the key to unlocking cosmic distances. Henry Norris' meticulous study of Cepheids in the small Magellanic Cloud had revealed a remarkable correlation. A direct relationship existed between a Cepheid's pulsation period and its apparent brightness. Cepheids with longer periods exhibited greater luminosity, while Leavitt's discovery provided a relative measure of distance. It lacked an absolute scale. The challenge remained to determine the intrinsic luminosity of these stars, a crucial step in transforming relative distances into absolute cosmic yardsticks. Hertzsprung recognized the profound implications of Leavitt's work. He embarked on a quest to calibrate the period-luminosity relationship, endeavoring to establish a zero point that would allow astronomers to calculate the absolute magnitudes of Cepheids, and consequently, their distances. The problem he tackled stemmed from the fact that Leavitt's observations were confined to the small Magellanic Cloud. She determined the relative luminosity of these stars, but she could determine the absolute luminosity of these stars. His approach involved a meticulous examination of Cepheid variables within our own Milky Way galaxy. By identifying Cepheids whose distances could be estimated through independent methods, such as parallax measurements or membership in star clusters with known distances, Hertzsprung could anchor Leavitt's relative period-luminosity relationship to an absolute scale. He essentially sought to bridge the gap between the apparent brightness of Cepheids and their true intrinsic luminosity. The technique Hertzsprung employed involved statistical parallax, a method for estimating the average distance to a group of stars based on their proper motions and radial velocities. Proper motion refers to the apparent angular motion of a star across the sky, while radial velocity measures its motion towards or away from us. By analyzing the proper motions and radial velocities of a sample of Milky Way Cepheids, Hertzsprung could derive an estimate of their average distance. This, in turn, allowed him to determine their average absolute magnitude, providing the crucial 0 point needed to calibrate the period-luminosity relationship. Hertzsprung's calibration efforts, while groundbreaking, were not without their challenges. The distances to Milky Way Cepheids were difficult to determine accurately, and the available data were often limited. He had to contend with the effects of interstellar extinction, the dimming of starlight by intervening dust and gas, which could affect the apparent brightness of Cepheids and introduce errors in distance estimates. Despite these challenges, Hertzsprung persevered, refining his methods and incorporating new data as they became available. His calibration of the Cepheid period-luminosity relation served as a cornerstone for subsequent distance determinations. The ability to measure distances to Cepheid variables provided astronomers with a powerful tool for probing the vast expanse of the universe. Cepheids became known as standard candles, objects whose intrinsic luminosity is known, allowing their distance to be inferred from their apparent brightness. Hertzsprung's work on Cepheids had a profound impact on the field of astronomy. His calibration of the period-luminosity relationship paved the way for more accurate measurements of distances to galaxies far beyond our own. Prior to this, the scale of the universe remained uncertain, with debates raging about the nature of spiral nebulae and their place in the cosmos. Were they simply clouds of gas within our Milky Way, or were they independent island universes located at immense distances? The calibration was crucial for Edwin Hubble's momentous determination of the distance to the Andromeda galaxy. Using the period-luminosity relationship calibrated by Hertzsprung, Hubble identified Cepheid variables within Andromeda and calculated its distance to be far beyond the confines of the Milky Way. This discovery shattered the prevailing view of a single, all-encompassing galaxy and established the existence of countless other galaxies populating the universe. Hubble was directly influenced by Hertzsprung's work, which provided the essential foundation for his distance measurements. Cepheid variable stars continue to serve as indispensable tools for modern astronomers. They provide a crucial rung on the cosmic distance ladder, allowing scientists to measure distances to galaxies millions of light years away. Refinements to the period-luminosity relationship have been made over the years, incorporating new data and accounting for factors such as meticity and interstellar extinction. Nevertheless, the fundamental principle remains the same. Cepheids offer a reliable and accurate means of gauging cosmic distances. The legacy of Hertzsprung's contribution to the understanding of Cepheid variables is firmly established. He transformed Henry Leavitt's discovery into a quantitative tool, providing the crucial calibration that unlocked the potential of Cepheids as standard candles. His work, in turn, had a transformative impact on our understanding of the scale and structure of the universe. Hertzsprung's meticulous study of Cepheid variables, refining the period-luminosity relationship, paved the way for another monumental contribution to stellar astrophysics, the collaborative development of the Hertzsprung-Russell diagram, often abbreviated as the HR diagram. This diagram, a cornerstone of modern astronomy, provides a powerful visual representation of the relationship between a star's luminosity and its spectral type or color. It serves as an indispensable tool for classifying stars, understanding their evolutionary stages, and inferring distances to stellar clusters. Prior to the HR diagram, astronomers grappled with the challenge of organizing the vast amount of data accumulating from spectroscopic surveys and parallax measurements, while spectral classification, pioneered by Angelo Secchi and refined by Annie Jumpkinnon at Harvard, provided a means of categorizing stars based on their surface, temperatures, and chemical compositions. A clear connection between spectral type and intrinsic brightness remained elusive. Hertzsprung, through his careful examination of stellar colors and magnitudes, began to discern a pattern. He recognized that stars of the same spectral type could exhibit a wide range of luminosities. He introduced the terms giant and dwarf to distinguish between these two groups, noting that stars with similar spectral characteristics could possess vastly different intrinsic brightnesses. This insight, published in a series of papers beginning in 1905, represented a crucial step toward unraveling the complexities of stellar populations. He plotted stars based on their absolute magnitude, derived from their distances, against their color indices, which serve as a proxy for temperature. This early work revealed a distinct grouping of stars, a main sequence, as it would later be known, along which most stars appeared to lie. Independently, Henry Norris Russell at Princeton University pursued a similar line of inquiry. Russell, focusing on stars with reliable parallax measurements, also sought to establish a relationship between spectral type and absolute magnitude. He presented his findings in 1914, showcasing a diagram that strikingly resembled Hertzsprung's earlier plots. Russell's diagram, however, incorporated spectral types directly rather than color indices and benefited from a larger sample of stars with well-determined distances. This allowed him to more clearly delineate the main sequence and identify the distinct populations of giant and dwarf stars. The convergence of Hertzsprung's and Russell's independent work led to the widespread adoption of the diagram that now bears their names. While both astronomers arrived at similar conclusions through different approaches, their combined efforts solidified the HR diagram's position as a fundamental tool in astronomy. It provided, for the first time, a comprehensive framework for understanding the diversity of stars and their evolutionary pathways. The HRI diagram is essentially a plot of absolute magnitude, a measure of a star's intrinsic brightness against either spectral type or color index, both of which are indicators of a star's surface temperature. Spectral types are traditionally arranged along the horizontal axis in the sequence O, B, A, F, G, K, and M, with O stars being the hottest and bluest and M stars being the coolest and reddest. Absolute magnitude, on the other hand, is plotted along the vertical axis, with brighter stars at the top and fainter stars at the bottom. When a large sample of stars is plotted on the HR diagram, a distinct pattern emerges. The majority of stars, approximately 90%, fall along the diagonal band known as the main sequence. These are stars that are fusing hydrogen into helium in their cause, the primary energy generating process in stars like our Sun. The position of a star on the main sequence is determined primarily by its mass, with more massive stars being higher, brighter, and located at the upper end of the main sequence, while less massive stars are cooler, fainter, and situated at the lower end. Above the main sequence lies a region populated by giant and supergiant stars. These are stars that have exhausted the hydrogen fuel in their cause and have evolved off the main sequence. As a star exhausts its core hydrogen, it begins to fuse hydrogen in a shell surrounding the core, causing the star to expand and cool, becoming a red giant. More massive stars can undergo further nuclear reactions, fusing helium and heavier elements in their cause, evolving into supergiants. Giants and supergiants are significantly more luminous than main sequence stars of the same spectral type, reflecting their larger sizes and higher energy output. Below the main sequence, in the lower left corner of the HR diagram, resides a population of white dwarf stars. These are the remnants of low to intermediate mass stars that have exhausted all their nuclear fuel and have shed their outer layers, leaving behind a dense top core composed primarily of carbon and oxygen. White dwarfs are extremely faint due to their small size, despite their high surface temperatures. The HR diagram's significance extends far beyond simple stellar classification. It provides a powerful tool for understanding stellar evolution, the life cycle of stars from their formation to their eventual demise. By tracking the positions of stars on the HR diagram, astronomers can infer their ages, masses, and evolutionary stages. For example, a star cluster, a group of stars formed at approximately the same time, will exhibit a characteristic pattern on the HR diagram. The most massive stars in the cluster will evolve off the main sequence first, followed by progressively less massive stars. By observing the turn-off point, the point on the main sequence where stars begin to deviate toward the giant region, astronomers can estimate the age of the cluster. The HR diagram also serves as a valuable tool for determining distances to star clusters and other astronomical objects. By comparing the apparent magnitudes of stars in a cluster to their absolute magnitudes inferred from their positions on the main sequence, astronomers can calculate the distance to the cluster using the distance modulus equation. This technique, known as spectroscopic parallax, provides a reliable means of measuring distances to objects beyond the reach of traditional parallax measurements. The HR diagram's influence on astronomy is immeasurable. It has provided a framework for understanding stellar populations, stellar evolution, and the structure of the Milky Way galaxy. Generations of astronomers have used the HR diagram as a guide in their research, and it remains a cornerstone of modern astrophysics. The diagram's enduring relevance stems from its ability to connect observable properties of stars, such as their brightness and color, to their fundamental physical characteristics, such as their mass, temperature, and age. The intellectual problem of stellar classification and understanding stellar evolution found a powerful solution in this diagram. It continues to be a fundamental tool taught in introductory astronomy courses and employed in cutting-edge research. Hertzsprung, building upon his earlier work and inspired by Russell's spectroscopic investigations, created a tool that continues to shape our understanding of the cosmos. The HR diagram, in turn, has influenced countless astronomers and remains a cornerstone of modern astrophysics and stellar evolution theory. Ejnar Hertzsprung's contributions extend far beyond the eponymous diagram that bears his name. His meticulous observations and insightful analyses shaped our understanding of binary stars, star clusters, and the very architecture of our galaxy. While the Hertzsprung-Russell diagram provides a powerful snapshot of stellar populations, Hertzsprung's other investigations reveal a broader commitment to unraveling the complexities of the cosmos. Binary stars, systems of two stars orbiting a common center of mass, presented a unique challenge to astronomers seeking to determine stellar masses and distances. Hertzsprung recognized the potential of eclipsing binaries, where one star periodically passes in front of the other, causing a dip in the system's overall brightness. By carefully measuring the timing and duration of these eclipses and combining this data with spectroscopic observations, he devised methods to calculate the stars' sizes, masses, and orbital parameters. This work provided crucial empirical tests for theories of stellar structure and evolution. His approach involved analyzing the light curves of eclipsing binaries, meticulously charting the changes in brightness over time. From these curves, he could infer the relative sizes of the stars, their orbital inclination, and the ratio of their surface brightnesses. Combining this information with radial velocity measurements obtained through spectroscopy allowed him to determine the absolute dimensions of the system, including the star's radii and masses. For example, his studies of the eclipsing binary system Algol, also known as Beer-Persei, provided some of the most accurate early determinations of stellar masses. The intellectual problem of accurately determining stellar masses, particularly for stars beyond the reach of parallax measurements, found a solution in his meticulous analysis of eclipsing binary systems. Hertzsprung's work on open star clusters, loose groupings of stars born from the same molecular cloud, further solidified his reputation as a master of stellar distance determination. He refined the moving cluster method, a technique that utilizes the convergent point of the star's proper motions to calculate the cluster's distance. Proper motion refers to the apparent angular motion of a star across the sky, measured in arcseconds per year. While individual stars may have small proper motions, the stars in a cluster share a common space motion, causing their proper motions to converge towards a distant point. By measuring the proper motions of cluster members and determining the convergent point, Hertzsprung could calculate the cluster's distance using simple trigonometry. His studies of the Hyades cluster, one of the nearest and best studied open clusters, were particularly influential. By applying the moving cluster method, he obtained a highly accurate distance estimate for the Hyades, which served as a crucial rung on the cosmic distance ladder, the sequence of techniques astronomers use to measure distances to increasingly remote objects. This precise Hyades distance allowed astronomers to calibrate calibrate other distance indicators, such as the period-luminosity relation of Cepheid variable stars, extending the reach of distance measurements to far greater distances. The challenge of accurately measuring distances to star clusters, a crucial step in calibrating the cosmic distance ladder, was addressed through his refined application of the moving cluster method. Hertzsprung's work on galactic structure, while less widely known than his contributions to stellar classification and distance determination, demonstrates his commitment to understanding the overall architecture of the Milky Way. He analyzed the distribution of stars and star clusters in the galaxy, searching for patterns and correlations that could reveal the galaxy's underlying structure. He recognized the importance of interstellar extinction, the dimming and reddening of starlight caused by dust particles in interstellar space, and attempted to correct for its effects in his analyses. He meticulously mapped the distribution of different types of stars, such as O and B stars, which are young, yet and luminous, and globular clusters, which are dense, spherical groupings of old stars. By tracing the distribution of these objects, he could infer the location of the spiral arms and the overall shape of the galactic disk. His efforts contributed to the growing realization that the Milky Way is a spiral galaxy, similar to other spiral galaxies observed in the universe. The complex problem of mapping the structure of the Milky Way galaxy, obscured by interstellar dust and vast distances, was tackled through his careful analysis of stellar distributions and his attempts to account for interstellar extinction. The enduring relevance of Hertzsprung's work lies in its emphasis on precise measurements, careful analysis, and insightful interpretation. He recognized the importance of combining observational data with theoretical frameworks, and he developed methods that are still used by astronomers today. His contributions to stellar classification, distance determination, and the study of stellar populations have shaped our understanding of the cosmos and laid the foundation for modern stellar astrophysics. His influence can be seen in the work of countless astronomers who have followed in his footsteps, using his methods and concepts to explore the universe. Hertzsprung's work was deeply influenced by Norman Poisson's meticulous observations of stellar brightness and his establishment of a magnitude scale, providing Hertzsprung with a quantitative foundation for his stellar classification efforts. Jacobus Captine's statistical studies of stellar motions and distributions, particularly his work on the concept of stellar streams, also influenced Hertzsprung's investigations of galactic structure. Henry Norris discovery of the period-luminosity relation for Cepheid variable stars provided Hertzsprung with a crucial tool for measuring distances to remote objects, which he skillfully applied in his studies of star clusters and galactic structure. His influence on others can be seen in the work of Henry Norris Russell, whose independent discovery of the Hertzsprung-Russell diagram solidified its importance in stellar astrophysics. Edwin Hubble, building on Hertzsprung's distance determination techniques, used Cepheid variable stars to measure the distances to galaxies, revolutionizing our understanding of the scale of the universe. Walter Baade, inspired by Hertzsprung's work on stellar populations, distinguished between population I and population for two stars, leading to a deeper understanding of stellar evolution and formation of galaxies. Ejnar Hertzsprung's legacy resides not only in the tools he created, such as the HR diagram and refined distance determination methods, but also in his rigorous approach to astronomical research. He demonstrated the power of combining precise observations with insightful analysis, revealing fundamental relationships between stellar properties and shaping our understanding of the cosmos. His work continues to inspire astronomers today, serving as a reminder of the importance of meticulous data collection, thoughtful interpretation, and a relentless pursuit of knowledge. His ability to connect disparate pieces of observational data into a coherent picture of the universe remains a hallmark of his genius, a legacy that continues to illuminate the path for future generations of astronomers.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.